Welcome back, everyone, to another journey into the fascinating world of probability and statistics. You're watching 99.73%, and today we are going to explore one of the most powerful concepts in all of statistics. Let's get started. As you can see, floating all around me, from rolling dice and flipping coins to complex distributions, randomness is everywhere. Today's topic is the core concept that connects all these chaotic events to mathematics, the random variable. But before we look at any equations, I have to tell you a secret. The term random variable is actually a very misleading name. Why? Because in reality, it is neither random nor is it a variable. Let's see exactly why. So, why isn't it a variable? Well, think back to your early days of basic algebra. When we see an equation like 2x plus 4 equals 10, that lowercase x represents a specific mystery number that we need to solve for. It's just hiding, waiting to be discovered. We do the math, we move things around, and boom, we find that x equals exactly 3. The mystery is solved. But in statistics, a random variable, which we usually write as a big capital X, is a completely different beast. Instead of a mystery number, it's much better to think of a random variable as a function, or even simpler, a translation machine. Its entire job is to take physical, real-world events and translate them into numbers. Think about a simple coin flip. The physical outcomes are just heads or tails. But math doesn't speak English. You can't calculate the average of the words heads and tails. That's where our machine steps in. It takes the outcome heads and perfectly maps it to the number 1. And it takes tails and translates it strictly to 0. It's a completely consistent, reliable role that acts as a bridge, turning a real-world event into a clean mathematical value. Now, let's see how this role actually looks visually. First, take a look at our sample space over here on the left, which is omega. Inside, you can see our physical, real-world outcomes. Next, we bring in the real number line, r. As we said, our goal is to step out of the physical world and into the realm of mathematics. Remember that translation we just talked about? Look at the arrows. These arrows visually represent that exact mapping. While the outcome of the coin toss might be totally uncertain and random, this rule, the arrow itself, is completely deterministic and always consistent. This entire connection, pointing from an outcome in the sample space directly to a number on the real line, is precisely what we call our random variable, x. It is simply a function that maps omega to r. And remember that secret from the very beginning? That's exactly why x itself isn't really random. This rule, this function, always works the exact same way. Now, at this point, you might be wondering, why do we even bother doing this? Why add this extra layer of complexity? Well, take a look at this equation right here. Mathematics only speaks the language of numbers. You simply cannot calculate the mean or the average of the letters h and t. But the very moment we use our random variable to convert them into ones and zeros, the magic happens. We can suddenly calculate averages, measure probabilities, and use the full power of statistical analysis. Okay, now that we have the theory down, let's look at a classic example to really cement this idea in your minds: rolling two fair dice. This is where you will see our translation machine really start to shine, because it takes something that seems random and scattered and turns it into something we can actually work with. You know, in many board games, we do not really care about the individual numbers on each die. What we actually care about is the total. So let's define our random variable x as the sum of those two faces. Imagine we roll the dice and get a 3 and a 4. Our function, x, takes that specific pair, adds them together, and then maps that outcome directly to the number 7. In that moment, our machine has successfully translated a physical event into a single, clean mathematical value. Now, take a look at this different outcome. If we roll a 2 and a 5, the sum is still 7. This highlights a really important point. Because our random variable is a function, it often acts as a many-to-one relationship. This means that several different outcomes from our sample space can all be mapped to the exact same numerical value. Whether we roll a 3 and a 4 or a 2 and a 5, the machine still translates them into the same number, 7. But what about the other end of the scale? If we roll a 1 and a 1, the function x maps this pair to the number 2. This is the smallest possible value our random variable can take in this entire experiment. Make sure to keep this specific mapping in mind because it is the starting point of our entire analysis. So far, we've seen how our random variable x translates specific outcomes, but to truly understand its behavior, we need to look at the bigger picture. Let's step back and build our entire sample space systematically. We start with that smallest possible roll we just saw, a pair of ones. But of course, that is just one single outcome. What else could happen? Well, we could roll a 2 and a 3, or maybe a 6 and a 6. Every time we roll, our random variable x is there, ready to translate that pair into a sum. If we map out every single possibility, we generate this beautiful 6 by 6 grid. This entire grid is our sample space, omega, consisting of exactly 36 unique, equally likely outcomes. Here is the formal mathematical notation for what we just did. Omega is the set of all pairs I and j. Our random variable, x, takes any outcome and outputs their sum, which is simply I plus j. Because the lowest sum is 2 and the highest is 12, the output of our function is clearly limited. We call this set of all possible output values the support of the random variable, denoted by s sub x. As you can see here, the support simply consists of the integers from 2 to 12. Now, let's set up these specific values as our main categories. Take a look at what happens when we group the entire sample space based on our random variable. Instead of 36 scattered pairs, x organizes them perfectly. You see, only one pair makes a 2, 2 pairs give us a 3, 3 pairs give us a 4, and so on, peaking at the number 7, which has 6 different combinations mapping directly to it. Let's calculate the actual probabilities. Since our dice are perfectly fair, every single cell in that triangle has exactly a 1 in 36th chance of happening. So what's the probability that x equals 2? Well, there's only one cell there, so the probability is simply 1 over 36. How about x equals 3? We have exactly 2 cells that give us a sum of 3, so its probability is 2 over 36. For x equals 4, we count 3 possible combinations, giving us 3 over 36. I think you see the pattern here. By repeating this simple counting process for all the remaining columns, we can build a complete probability mass function table, or PMF. This table summarizes absolutely everything we need to know about the behavior of our random variable. Numbers in a table are great, but visualizing them is even better. Let's take all this data and plot our PMF chart. First, we set up our horizontal axis for the values of x and our vertical axis for the probabilities. Watch as the bars start to appear one by one. We begin with x equals 2, then we move to 3, and we continue this for every value in our support. As we fill them all in, this beautiful, perfectly symmetric distribution chart begins to emerge. The height of each bar represents the probability of that specific sum. You can clearly see that the number 7 is the tallest bar of all. That is simply because our random variable funneled the highest number of physical combinations directly into it. All right, let's level up a bit. We are moving on to a slightly more advanced scenario. For this one, I have brought in this lottery spinner for us. Picture this rotating drum filled with colored balls. Specifically, we have 4 red balls, 3 blue ones, and 3 green balls. This setup is a perfect way to see how a random variable handles a more dynamic situation. Our random experiment consists of drawing exactly 2 balls at random from this spinner without replacing them. Now, let's put them back for just a moment, because before we do this for real, we need to set up something highly important. I am going to assign a unique number to every single ball, making each one completely distinct and distinguishable from the rest. Why on earth do we do this? Well, if we only look at the colors, the outcomes are not equally likely. But by numbering them, we transform our problem and create an equally likely sample space. With our balls now uniquely numbered, let's look at the entire sample space, omega. Since we have 10 distinct balls and we are choosing 2 of them, we use our combination rule, 10 choose 2, which equals exactly 45 total outcomes. And because every single pair is now equally likely, the probability of drawing any specific omega is simply 1 over 45. Okay, let's define a brand new random variable, y. For any pair of balls we draw, y will simply be the number of blue balls minus the number of red balls. Notice that the green balls act as zeros in this equation. By doing this, we find that the total set of all possible outputs, the support of y, ranges from -2 to +2. Now, let's calculate the probabilities. What is the probability that y equals -2? Well, looking at our rule, this only happens if we draw exactly 2 red balls. Since we have 4 red balls in total, we must choose 2 out of those 4. Doing the math, 4 choose 2 gives us exactly 6 combinations. Therefore, the probability is 6 over 45. Moving on to y equals -1. This happens when we draw 1 red ball and 1 green ball. That is, 4 choose 1 times 3 choose 1. This gives us 12 combinations, making the probability 12 over 45. Now let's look at a more interesting case. What about y equals 0? This is a special case because it can happen in 2 completely different ways. Either we draw 2 green balls, which is 3 choose 2, or we draw exactly 1 red and 1 blue ball, which is 4 choose 1 times 3 choose 1. Adding those possibilities together gives us 15 total outcomes, so the probability for y equals 0 is 15 over 45. Following the same logic for y equals 1, we need 1 blue ball and 1 green ball. 3 choose 1 times 3 choose 1 gives us 9 combinations, so the probability is 9 over 45. And finally, for y equals 2, we must draw exactly 2 blue balls. 3 choose 2 gives us 3 combinations, so the probability is 3 over 45. And there we have it. We have successfully translated our lottery experiment into a complete probability mass function. Now, plotting this data gives us this beautiful bar chart. We start with the bar for y equals -2 and watch as the rest of the distribution emerges. Notice something different here? This chart leans slightly to the left. It is not perfectly symmetric like our dice example. Why is that? Well, that is simply because we started with 4 red balls, but only 3 blue ones, which naturally pulls our results toward the negative side. And as a final sanity check, if we add up all the probabilities in our distribution, they equal exactly 1. This confirms that our random variable safely accounted for every single possible outcome in our entire sample space. So let's wrap this all up. A random variable is, at its core, the ultimate mathematical translator. It takes chaotic real-world events and brilliantly organizes them into clean, manageable numbers. Thank you so much for watching, and I will see you in the next one. And speaking of the next one, in our upcoming video, we take everything you've learned here and go deeper. We're talking about discrete random variables, the real mathematical machinery behind the patterns you've already started to see. See you there.